Hi everyone, welcome again to the course of structural biology. This is we are continuing with the structural biology techniques. We are talking about X-ray crystallography, and today we are going to discuss about phase problem, Patterson function, how to solve phase problem, heavy atom replacement methods to solve phase problem, and some techniques relating to heavy atom replacements, which are isomorphous replacement, anomalous dispersions and all. I will start where we end in the previous class. Few formulas we have picked up and these are important. One is the phi equal to 2 pi h x plus k y plus L z, f h k L equal to square root of summation j f j cos 2 pi h x j plus k y j plus L z j square plus summation j f j sin 2 pi h x j plus k y j plus L z j square. This we call formula 2, which is reduced to j equal to 1 to n f j e to the power 2 pi I h x plus k y plus L z. That is the formula 3, which is about structure factor. The fourth formula is about electron density rho x y z equal to 1 by v minus infinity to plus infinity summation f h k L e to the power 2 pi I h x plus k y plus L z minus phi h k L. I would also talk little bit about the real space and reciprocal space, which we discussed in detail while we are talking about crystal lattice. In the real space we get information about unit cell A, B, C and alpha, beta, gamma, the distance and angles, electron density which I just talked about rho x y z, atomic coordinates x y z, thermal parameters B, which we will talk later in details, bond lengths in angstrom, bond angles in degrees, crystal faces. Whereas, from the reciprocal space we will get to know about diffraction pattern, reflections, integrated intensities which is I h k L, structure factors f h k L, phase alpha h k L. I would also like to talk about some correlation. So, if you see throughout the story while data collection, data processing, talking about crystal, unit cell, lattice, what we are talking about, from a crystal we get the information of 3D lattice in direct space, whereas this we talked a lot about. So, you know that this is a diffraction pattern. From a diffraction pattern, this is representing a 3D lattice. So, the crystal is representing a 3D lattice, the diffraction pattern is also representing a 3D lattice, but where this is a 3D lattice in direct space, this is the 3D lattice in the reciprocal space, and the conversion from crystal to diffraction pattern is the diffraction experiment, whereas when you want to do the theoretical calculation, this is the Fourier transform. Similarly, this is electron density and this is the structure factor. These are also interconvertible in experimental term diffraction, whereas in theoretical term Fourier transform. If we now consider the entire thing, it definitely start by getting a pure protein, but then the process of crystallography start after getting a crystal. So, from crystal to obtaining a diffraction pattern by diffraction by applying X-ray, then from diffraction pattern the intensity of spots would give us the structure factor, and then from structure factor by inverse Fourier we get electron density. Also the relation of electron density and structure factor, now we know the formula, whereas the structure factor F HKL equal to J equal to 1 to n, the n number of atoms, F J which is the contribution of individual atomic scattering factor, E 2 pi I H x plus k y plus L j, whereas the electron density rho x y z equal to 1 by V minus infinity to plus infinity H K L, structure factor F H K L absolute value e to the power 2 pi I H x plus k y plus L z minus phi H K L. Now we know that F H K L have two term F j and exponential value of minus 2 pi I H x j plus k y j plus L z j. So if you see that F j summation is giving us the absolute value of the structure factor, which is amplitude which comes directly from the diffraction pattern. The other term is phase. From an X-ray diffraction experiment which we have discussed in detailed, we can measure the amplitude, but we get no information about the phase. So, we get this, but we do not get information. Is it we do not get it, what else? Today we will discuss about that. But more importantly, as we are getting the amplitude and do not get the phase, so that is making us unable to calculate electron density. This is called the phase problem, and you all know now phase problem is a very critical and famous problem in the field of protein crystallography. So, in order to calculate an electron density map, we require both the intensities and the phases of the reflection. The information content of the phases is appreciably greater than that of the intensities. Unfortunately, it is almost impossible to measure, derive the information of the phases experimentally, and this is known as the crystallographic phase problem and would appear to be unsolvable, very important. And when we are talking about that, we have to introduce Arthur Lindo Patterson. So, the impossibility of measuring the relative phases among the diffracted beams phi HKL makes unfeasible a direct calculation of the electron density function. Without this, it could be impossible to find the atomic position within the unit cell. The problem was solved only after in 1934 when Patterson introduced his brilliant idea, thereby obtaining the first solution to the phase problem. What is his idea? We are going to discuss in details. Structure solution in absence of phase, the Patterson function. The structure of small molecules may be solved even in the absence of phase information. As we know that the phases determine the positions of the peaks of electron density across the unit cell, and therefore, it could also determine the position of the atom, right. But the presence of a strong diffraction spot alone give a strong indication that features must be present with the corresponding spacing. Thus, the structure factor magnitudes alone contain information about the spacing of atoms in the structure. So, we have discussed, but just to your memory refreshed, if you see what is the amplitude is if you look at the diffraction pattern, you see there are different spots dot 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 dot, the patterns. Some of the dots are very intense, whereas some of the dots are not so intense, right. So, from there you get the intensity, which is I square, which is proportional to the structure factor. But also if you see, there is a pattern, the space difference, the difference between the space of the dots. If you remember, when I was talking about the phase comes because of these differences. So, from the diffraction pattern, it could also, there is a chance that we could have gained some information about the phase. This information may be accessed by calculation of the Patterson function. The Patterson function is obtained by calculating a map using the squared structure factor magnitude and all the phases set to 0. We will show the mathematics. Instead of peaks at the atomic position, the Patterson map shows peaks at every position that correspond to an interatomic vector in the structure. The Patterson function has been an effective tool for solving small molecules. However, its usefulness falls quickly as the number of atoms increases. So, it is possible you get to calculate it without getting the information about the phase, but more the atoms coming, more complexity, the method get to be less effective. For a structure of n atoms, the Patterson function will contain n to 1 interatomic vectors, many of them overlapped. This approach becomes unusable for structure of more than 20 to 50 atoms unless there is a subset of atoms with high atomic number. So, two things: one, for small molecule this is good, you understand it. A second thing is coming, which is great and which is now for what in protein crystallography Patterson is used. That is, if you see again, this approach becomes unusable for structure of more than 20 to 50 atoms. So, for structures of 20 to 50 atoms usable, but this is one part. The second part is, unless there is a subset of atoms with high atomic number. So, in protein, if you remember, and I will talk about this, there is carbon, there is nitrogen, there is oxygen. Now, if you put a mercury, intensity is much higher. So, you have a chance of using it. You get it? That is one of the key factor. Patterson derived his function P u v w. So, now this x y z is changing to u v w by introducing some modifications into the electron density function. How? Let us take a look. So, this is rho x y z, we know x y z 1 by v minus infinity to plus infinity f h k l e to the power minus 2 pi I h x plus k y plus L z minus phi h k l. Patterson function, definitely it is u v w as I talked, P u v w 1 by v minus infinity to plus infinity f h k l square. So, it is squared cos 2 pi h u plus k v plus L w. So, in one thing this is squared. As a result of this derivation, the structure factors represented by their amplitudes and phases are replaced by the squared amplitudes whose values are proportional to the diffracted intensities. So, there is no phase and the amplitude is squared. and this comes to ultimately to the formula FHKL absolute value square equal to I HKL, I is the intensity, which is FHKL whole square, KALP, who are K is the scale factor, A is the absorption factor, L is the Lorentz factor, and P represent the polarization factor. So, the Patterson function can be directly calculated from the experimental data obtained in the diffraction experiment, because now we do not see the involvement of a phase. However, the issue is to obtain the atomic coordinates from this new function. The information provided by the maxima of the Patterson function correspond to a map of position vectors, which are relative positions between each pair of atoms in the structure. The value of the function at this maxima is proportional to the product of the implied atomic numbers, which provides a clear advantage for detecting vectors between heavy atoms, that is atoms with a large number of electrons. We will again discuss this, but you could easily now understand that carbon, nitrogen, oxygen. Now, if you include transition metals, mercury, gold, platinum, you have a lot of electrons, and that gives a lot of intensity, because in this method intensity plays a huge role. The scattering, where you have importance of number of electrons. Suppose the crystal space is defined by the value of rho function at every point in the unit cell given by the coordinates x, y, z. Patterson space, which is also periodic and defined by a unit cell which is identical to the crystal unit cell, is defined by the generic coordinates u, v, w. The relation would be described in such a way that any pair of atoms in the crystal located at x1, y1, z1 one point and x2, y2, z2 another point will be shown in the Patterson map by a maximum with coordinates u, which is x1 minus x2, v, which is y1 minus y2, w, which is z1 minus z2. So, if you see the points x1, y1, z1 and x2, y2, z2 coordinates, here you will see how the UVW is coming, as we already talked about. U is x1 minus x2, V is y1 minus y2 and W is z1 minus z2. The positions of this maxima represent the differences between the coordinates of each pair of atoms in the crystal. So, the position of this maxima, this is the difference. At the origin, which is 0 0 0, there is a high maximum corresponding to the interatomic vector of each atom with itself. Let us discuss some. So, we now understand mathematically how the UVW change of this equation and how it put actually a lot of importance on the diffraction amplitude, neglecting the phase. Patterson function is defined in a periodic space whose unit cell is identical to the crystal unit cell. It shows a high density of peaks because of the maxima, that is the function contains a high number of maxima. The Patterson function of a crystal formed by n atom in the unit cell will show n square maxima, all possible interatomic vectors, and even discounting the vectors, if you do that, of each atom with itself, the number would be n square minus n. In addition, and due to the fact that atoms are not punctual, they have a volume, there will be many vectors between their profiles, and therefore the interatomic peaks will be wide, producing some overlap among the Patterson peaks. You could see that here it would be wide and there are overlaps if you compare between the crystals, the peaks and the Pattersons. The height of the peaks is proportional to the product of atomic numbers of the atoms involved. Therefore, the highest maxima in the Patterson function correspond to vectors between atoms with highest atomic numbers, again giving advantage to the heavy atoms. This fact provide a great advantage in detecting the heavier atoms in a structure. So, if you see, this is the atoms in the crystal unit cell, this is the interatomic vectors in the crystal unit cell, and this is the Patterson function. Also, if you see, I talked about this in the symmetry topic. If you look at this point, everyone is same and equidistant. So, this is a inversion center. We get a inversion center or center of inversion I, and it would be very important when we are now talking about the symmetry. The symmetry of the Patterson function or the symmetry of the Patterson space is higher than one of the electron density function, the crystal. As a result, if the crystal symmetry can be represented by one of the 230 space groups, which you already know, the corresponding Patterson symmetry will be represented by only 24 space groups. This simplification is due to the loss of information that occurs when the structure factors in rho x y z are replaced in the p u v w function by the squared amplitudes only. Also, in Patterson function, if there is a vector from atom 1 to atom 2, there will be another vector identical, but in the opposite direction from atom 2 to atom 1. This means that the Patterson function is always centrosymmetric. Talking about the direct methods to solve the phase problem, for small and intermediate sized molecule, the atoms are normally well ordered, and as a result structure factors may be measured to very high diffraction angles. The high angle diffraction spots give information about finely spaced features in the unit cell. In this case, the missing phase information may be reconstructed directly from mathematical relationships between the structure factors. Let us think about like NaCl crystal or something. Here you know that you have only two atoms, sodium and chlorine, and you know their nature and all. So, and you also know the space and all. So, you could reconstruct actually, they are less complex. Since the phases come directly from the observed diffraction pattern, these methods are referred to as direct methods. The phase relationships on which direct methods rely depend on placing constraints on the electron density in the unit cell, for example, that it is everywhere positive or that it is clumped into a distinct atomic peaks. So, like when you have very complex like a protein, it is difficult to find them out, but when you have small molecule, you know the information also, it is easier. If one structure factor is known in both magnitude and phase, then it can be inferred that atoms are more likely to be located in some regions of the cell and less likely to be in other regions. That is what I was talking about, the small molecules where the informations are simpler and it is more regular, it is more definitive and all. These places restrictions on the possible phases of other structure factors, which must reinforce likely areas in order to produce sharp peaks at the atomic position. So, in one way it is simpler and all, and there as if you imagine, if there is NaCl as we are talking about, there would be more redundancy. So, peak intensity would be more and all those things. The strongest relationship of this form is the three phase invariant. In this case, the constraints of positivity and atomicity imply that when three reflections whose Miller indices sum to 0 are strong, the phases of those reflections must sum to a value near 0. A direct method calculation might then proceed as follows: 1. phases are chosen for a few strong reflections, then phases for other reflections are generated using phase relationship among strong reflections. Once enough phases have been calculated, the electron density may be calculated and can be interpreted in terms of atomic positions. So, first the phases are chosen for strong reflections because they are easy to get, then phases for other reflections are generated using phase relationship, the mathematical relationship among strong reflections. Once enough phases have been calculated, the electron density may be calculated and can be interpreted in terms of atomic position. Unfortunately, the phase relationship become weaker as the number of atoms in the structure increases. Furthermore, this approach only works when data can be collected to high resolution. So, the requirements are simpler compounds with less number of atoms and high resolution. The use of multi-solution method, by which a larger set of starting phases is chosen at random and the calculation is repeated many times until a reasonable structure is obtained, has allowed direct methods to solve structure of up to 2000 atoms. Let us get a summary of this. So, there are three methods. One is called Dirac method, one is called Patterson function based method, and another is called brute force method. If the crystal diffracts to high resolution less than 1.2 angstrom, the initial phases can be estimated using direct methods. Direct methods can be used in X-ray crystallography, neutron crystallography and electron crystallography. A number of initial phases are tested and selected by this method. The other one is Patterson method, which directly determines the position of heavy atoms. The Patterson function gives a large value in a position which corresponds to interatomic vectors. This method can be applied only when the crystal contains heavy atoms or when a significant fraction of the structure is already known. For molecules whose crystals provide reflection in the sub-angstrom range, it is possible to determine phases by brute force method. In this method, we have to test a series of phase values which would be performed until spherical structures are observed in the resultant electron density map. So, this is about the direct method and their possibilities, advantages, disadvantages. Again come back to the phase problem. Why the phase problem technically happened? We have seen that when waves are diffracted from a crystal, they give rise to diffraction spots. Each diffraction spot corresponds to a point in the reciprocal lattice and represents a wave with an amplitude and a relative phase. But in reality, what happens is that photons are reflected from the crystal in different directions with a probability proportional to the square of the amplitude of this wave. We count the photons and we lose any information about the relative phases of different diffractions. So, we count the photons, but we lose any information about the relative phases. In physics, the phase problem is the problem of loss of information concerning the phase that can occur when making a physical measurement. Light detectors such as photographic plates or CCDs measure only the intensity of the light that hits them. This measurement is incomplete, and when I say incomplete, we are even neglecting other degrees of freedom such as polarization and angle of incidence, because a light wave has not only an amplitude, but also a phase which is systematically lost in the measurement. In diffraction or microscopy experiments, the phase part of the wave often contains valuable information on the studied sample. The phase problem constitutes a fundamental limitation ultimately related to the nature of the measurement in quantum mechanics. In X-ray crystallography, which is our topic, the diffraction data when properly assembled gives the amplitude of the 3D Fourier transform of the molecule's electron density in the unit cell. If the phases are known, the electron density can be simply obtained by Fourier synthesis. This Fourier transform relation also holds for two-dimensional far field diffraction patterns, giving rise to a similar type of phase problem. This two-dimensional phenomenon is popularly called as Fraunhofer diffraction. So, if you see the figure A, there are 4 atoms and 2 Bragg's plane. Now, if we try to draw a figure like the figure A showing the position of the atoms in different colors. So, 4 color is showing 4 different atoms. It shows again how the phase and amplitude of the overall scattered wave arise from the individual scattered wave. So, every atom have their scattering, right. There are 4 atoms and 2 Bragg's planes. The relative phase from 0 to 360 degrees depends on the relative distance of the atoms between the planes that define a phase angle of 0. So, if you look at the plot of imaginary and real in the figure B, the atoms and their contributions to the scattering are shown in matching colors. So, if you see the pink one, this is the pink one, you see the green one, this is the green one, if you see the orange one, this is the orange one, the blue one, this is the blue one. The overall scattered wave is represented by a black vector, which is the sum of the other vectors. This is the sum of the all other atoms vector. The vector amplitude and phase, or more properly the complex number representing the overall scattering from a particular set of Bragg planes is termed the structure factor, and it is usually denoted as A bold, because it is bold to tell you this is a complex number. It turns out that the structure factors for the various points on the reciprocal lattice correspond to the Fourier transform of the electron density distribution within the unit cell of the crystal. A very convenient property of the Fourier transform is that it is reversible. If you apply an inverse Fourier transform to the structure factor, you get back the electron density, which we have discussed earlier. So, we measure a diffraction pattern, take the square root of the intensities, and we are stuck. If we knew the phases, we could simply compute a picture of the molecule, but we have lost the information through our experiment. So, we talked about what is the problem. Now, through theory, we try to understand that this is the phase problem, and a large part of the development of crystallography is devoted to solving it. So, this is electron density equation. Need to solve the equation for all x, y, z in the unit cell. What do we know? We record the P, the position, the triple index HKL, and intensity IHKL, which is proportional to the structure factor square of each reflection, which is we get from the spots in the detector, the diffraction pattern. As we talked about, the measured intensities are proportional to the coefficient of the electron density equation. So, from the structure factor equation, we can see that if we know the contents of the unit cell, we can calculate FHKL. But actually we are dealing with the inverse problem. We have information about FHKL, we got it from the intensity from the spots, but need to know the content of the crystal. We have FHKL and we want to get the electron density, which will help us to spot the atoms to understand what is there in the crystal. The structure factor equation is periodic and is represented a Fourier series. taking the Fourier transform of the equation for FHKL, we get the necessary equation. This is the equation of electron density, which describe the electron density of the crystal. So, the Fourier transform of the diffraction data gives us a representation of the contents of the crystal, and note that the FT of the Fourier transform of the content of the crystal give us the diffraction pattern. So, let us take an example, an atom and its Fourier transform. So, if this is an atom, the Fourier transform will be like that. So, both functions have circular symmetry. If you see, the atom is a surf feature, whereas its transform is a broad smooth function. This illustrates the reciprocal relationship between a function and its Fourier transform. Now, we take a bigger molecule. A molecule consists of 7 atoms and its Fourier. Its transform shows some detail, but the overall shape is still that of the atomic transform. We can consider the molecule as the convolution of the point atom structure and the atomic shape. Thus, its transform is the product of the point atom transform and the atomic transform. Now, we are going from there to crystal and we start getting a pattern. Finally, we build up a crystal by convoluting the molecule with the grid. The result is a crystal structure. The Fourier transform of the crystal is thus the product of the molecular transform and the reciprocal lattice. We also talked about this, and this is the diffraction pattern. So, now if you have pictures and which have phase and amplitude, if we take amplitude or color of a picture from the duct transform, so these, and we get phases brightness from the cat transform. You see that you could see the cat, that means good phases are more important than good amplitude. So, what are the method to solve the phase problem? Direct method we have discussed already. Another two categories are experimental phasing, where we will use heavy atom, and the third one is molecular replacement, which requires some prior knowledge of the crystal structure you want to solve. Why? Because molecular replacement, which I will talk in detail in the next class, is a revolutionary step in the field of protein crystallography. Today you see the number of crystal solving, every day new crystals are coming, thanks majorly to molecular replacement. Molecular replacement is kind of a hybrid technique, taking the concept of theory and experiment together. It is a great contribution from Michael Rossmann, and we will discuss in detail about these and its effect, its role in changing protein crystallography. But now we will go and discuss about experimental phasing. So, experimental phasing means, if you remember, I am constantly talking about, you have carbon, nitrogen, oxygen in the crystal, you need some others, and the solution comes through the transition metals. So, the use of heavy atom substitution was invented very early on by small molecule crystallographers to solve the phase problem. The isomorphous crystals crystals which are same type like CuSO4 sulfur and CuSeO4 selenium. Two copper complexes, one is made of sulfur, one is made of selenium, was first one to be solved using the technology of isomorphous replacement. The changes in intensities of some classes of reflection were used by Beavers and Lipson to locate the copper and sulfur atom. It was Max Peruz and John Kendrew who first applied the methods to proteins, Peruz in 1956 and Kendrew in 1958, and I hope that you remember while we start crystallography, we talked about these two guys who have solved the first protein crystals. They have performed soaking protein crystals in heavy atom solutions to create isomorphous heavy atom derivatives, same unit cell, same orientation of protein in cell, which give rise to measurable intensity changes which could be used to deduce the position of the heavy atoms. What is isomorphous replacement? The isomorphous replacement method is based on the experimental data sets of two or more structures differing only in the presence or absence of some atoms or in the presence of some atom of a different kind. Multiple isomorphous replacement or MIR is historically the most common approach to solving the phase problem in X-ray crystallography studies of protein. For protein crystals, this method is conducted by soaking the crystal of a sample to be analyzed with a heavy atom solution or co-crystallization with the heavy atom. So, I talked about, but if you do not remember, when we get a crystal, we could soak a small molecule or a heavy metal into it. Is this a challenging process? Yes, it is a very challenging process which I am going to discuss little bit in the next class, but this is probably the only way. The another alternative is when you are growing a crystal, you remember the drops we set up, hanging drop, sitting drop. While we are doing the screening, we add heavy atoms there. So, the first one where after the crystal is formed, you do the process is called soaking. You soak it. Okay, you have a solution of heavy metal and you put the crystal there. So, the crystal could soak a heavy metal. Another one is co-crystallize, you add the heavy metal inside the protein, so they could crystallize together. The addition of the heavy atom or ion to the structure should not affect the crystal formation or unit cell dimension in comparison to its native form, hence they should be isomorphic. So, if they affect, you cannot continue with this. How to know? Again we will discuss in the next class. So, you remember this, I talked about that there are 4 atoms, they contribute and the black vector is representing the sum. So, these represent structure factor of the protein Fp. When you add the heavy atom, here is the heavy atom, what you get? You get Fp and you get FH. So, you get so you have the you got Fp when you have the native data set, and now in presence of this heavy atom you get a different structure factor FPH, which is Fp plus FH, as you could see here. So, introducing a heavy atom into a crystal is isomorphous differences. So, two protein diffraction patterns shifted vertically relative to one another. One is from native bovine beta lactoglobulin, I am coming to that, and the other from a crystal of the same protein soaked in a mercury salt solution. So, as a metal, heavy metal, we are using mercury. So, what we have to see, intensity changes for reflection in the latter, identical unit cells suggesting isomorphism, as I discussed in the last slide, del F equal to FPH minus FP. So, if you look at here, you see that there are sets. Some of the sets, like if I take these sets, are stronger and some are not so strong. So, what happened here, addition of one mercury atom to a protein of 1000 atoms will produce an average fractional change of intensity of 25%. So, differences should be easy to measure. So, the intensity difference, the del I by I equal to square root of NH, the number of heavy atom, to NP FH by FP. FH is the contribution of scattering from the heavy atom, FP is the contribution of scattering from the protein. We can use isomorphous differences to derive phase information via isomorphous replacement. I would talk about details mathematics again in the next class, but now we will talk about a different thing, which is anomalous dispersion, which affect the scattering factor. In a first approach, the scattering power of the different atom does not depend on the wavelength of the X-ray radiation. However, there are side effects that make them different. How? If the incident X-ray radiation has a frequency close to the natural oscillation frequency of the electrons of a given atom, there occurs the so called anomalous dispersion, which modifies the atomic dispersion factor. We discuss about this. In this situation, the expression of scattering factor is modified with two terms, F prime and F double prime, which represent the real and imaginary components respectively of the anomalous fraction of the atomic scattering factor. So, it changes. If you see, that is how it changes. In protein crystallography, anomalous scattering refers to a change in a diffracting X-rays phase that is unique from the rest of the atoms in a crystal due to strong X-ray absorbance. The amount of energy that individual atoms absorb depends on their atomic number. The relatively light atoms found in proteins such as carbon, nitrogen and oxygen do not contribute to anomalous scattering at normal X-ray wavelengths used for the X-ray crystallography. Thus, in order to observe anomalous scattering, a heavy atom must be native to the protein or a heavy atom derivative should be made. So, first of all, you understand anomalous dispersion, anomalous scattering, it is a effect and due to strong X-ray absorbance, and this is not affecting carbon, nitrogen, oxygen. So, you need a heavy atom to do that, a metal again, and understand in order to observe anomalous scattering, a heavy atom must be native to the protein or a heavy atom derivative should be made. So, what is native? There are some proteins which we are called metalloproteins. In those proteins, zinc, iron in their different oxidative state are present, like for iron this is cytochrome P450. So, like that, and there are different DNA binding protein which have zinc fingers. So, they are native, but if it is not native you have to develop heavy atom derivatives. In addition, the X-rays wavelength should be close to the heavy atom's absorption edge. So, you have to choose the heavy atom according to that. MAD is called multiple anomalous dispersion. In this technique, atoms' inner electrons absorb X-rays of particular wavelengths and remit the X-rays after a delay, inducing a phase shift in all of the reflections known as the anomalous dispersion effect. Analysis of this phase shift, which may be different for individual reflections, results in a solution for the phase. So, getting phase is a comparison, anything, any difference with a element with high electron content, with the element with anomalous, anything the differences make, you are getting into your solution. MAD depends on the presence of sufficiently strong anomalously scattering atoms in the protein. Like as I talked about zinc, if you have one zinc and your protein is huge, then the presence of the zinc atom with respect to the carbon, nitrogen, oxygen would be much low, you do not get good signal. Anomalous scattering occurs if the electrons in an atom cannot be regarded as free electrons. An anomalous scatterer absorbs X-rays of specified wavelength. As a result of this absorption, Friedel's law does not hold, that is, the reflection H k L and minus H minus k minus L are not equal in intensity. This inequality of symmetry related reflection is called anomalous scattering. Now, selenomethionine is a wonder. In case of methionine, there is sulfur. The sulfur is replaced with selenium in some bacteria who probably adopt themselves in very high selenium condition. That codon is utilized in the field of protein engineering to be introduced, so that whatever methionines are there is changed to selenomethionine. It was discovered by Theresa Stadman. Selenocysteine, so I talk about selenomethionine, another sulfur selenocysteine. Selenocysteine is present in several enzymes, glutathione peroxidases, tetraiodothyronine 5' deiodinases, thyroidoxine reductases, formate dehydrogenases, glycine reductases, selenophosphate synthetase 2, methionine R sulfoxide reductase B1 or Sepex 1 and some hydrogenases. The biochemical utility of selenocysteine was described by biochemist Robert Hundal from University of Vermont and chemist Hans Reich, University of Wisconsin, Madison. So, as I told, it is a naturally occurring amino acid. The L-selenomethionine enantiomer is the main form of selenium found in Brazil nuts, cereal grains, soybeans and grassland legumes. Selenomethylselenocysteine is the major form of selenium found in Astragalus, Allium and Brassica species. So, this is the structure, you see the sulfur is replaced by selenium. Incorporation of selenomethionine into protein in place of methionine aids the structure elucidation of protein by X-ray crystallography using method of anomalous dispersion. So, here you introduce the codon and then it would be having those selenium. Selenium is a metal, it is giving you a lot of electron, and you solve the structure by using anomalous dispersion. Metalloproteins structures have been solved with multiple anomalous diffraction. Proteins that do not naturally contain anomalous scatterers can be expressed in E. coli in a defined medium with selenomethionine or selenocysteine. The selenium atoms serve as anomalous scattering heavy atom here. The caveats are MAD requires a tunable wavelength. The data collection can only be done at synchrotron radiation facilities. So, if you remember when I was talking about X-ray sources, I talked about two type of sources. One is the synchrotrons, which are limited and present in advanced or developed countries. Like in India, we do not have synchrotron source to collect X-ray data for protein. We are working using our home sources, and you cannot do this type of experiments using home sources. So, today we have discussed about phase problem, from where the phase problem is generated, how we could take the help of direct methods, especially Patterson, to solve the phase problem. We also discussed the technicality of the phase problem, and then we discussed about Patterson function, how it is applied, how it is applied for small molecule, how it is applied for protein, especially when we are working with heavy atoms. We discussed about other direct methods. We discuss about how the problem could be solved by indirect methods, which are heavy metal incorporation experiments. We talked about isomorphous replacement, we talked about metal oriented anomalous scattering. We will discuss about other methods in the next class. Please keep listening and keep asking questions if you are having any doubts about that. Thank you very much.